So we begin looking at part 3 of our 3-part series by talking about arrays and vectors. And vectors are just smart dynamic arrays. So let's take a look at this kind of stuff. So an array is a variable that can store multiple values of the same type. Everything is stored in contiguous memory, item for item. So it's one block of memory, and it's declared using the square bracket operator. So in this case, just like they have, is like int values, and then I could put 5 inside of there, and if I hit the breakpoint, run my program, none of it's initialized, but you can see I mouse over values, and you can see this is the pointer to the first memory address, because that's what int, it's a contiguous block of memory, so all I need to do is get access to the first byte, and then I should be able to get all the other bytes. There's 20 bytes used, 4 bytes per int times 5, but they're uninitialized, and so that's this negative 858 million is generally what's used, at least in this mode of development, when it comes to what is the value that's stored in these memory locations. It's essentially uninitialized, but Visual Studio does technically initialize it when you're in debug mode, but whatever, it's just a silly little detail. So as I was showing you here, each element is, in this case, it's 4 bytes of storage, stores a completely distinct element. So it's just a way of getting around it, like so I don't have to create 5 separately named variables, A, B, C, D, E. And you're like, well, that doesn't sound too bad. And for 5, it doesn't sound too bad. But what if I wanted 10,000 of them? What if I wanted 1,000,000? It's a video game that has 14,000 or 14 million different something or others. That's a problem. So we would definitely want to use numbers instead of having to write for the rest of our lives every single variable name. Could you imagine writing the code that can handle that too? So that's where this is coming from. This is a way of simplifying when we have multiple pieces of data to work with here. And so we have to put a hard-coded number here because this is calculated at compile time. The compiler figures out how much storage space is needed. So if I do something like int, I'll do size equals 5, I can't do this because even though this is a variable and it's the line right before, the compiler doesn't truly know that because it's not a constant value, it's a variable number, the compiler can't figure out how much space to set aside for the thing. So you can do this, you just have to throw the word const on it, because then the compiler knows that this number is never going to change inside the program, and so because of that, the compiler can figure out how much storage space to set aside. Okay, so again, int is 4 bytes, 5 elements, so that's how you know it's 20 contiguous bytes. And in this case, like in the same kind of stuff, long double, if long double is 8 bytes and there's 10 elements, then that's how you get to 80 bytes for that kind of thing. So accessing array elements, then in this case, if I wanted to set everything up, I could say values sub0 equals 99, and then I could use it, I could get the information out of it and say print out values at the 0 location. And that'll print 99, of course, because that's what I'm doing. This is putting information into it, and this is getting information out of it. And so one big point to notice then, humans start counting from 1, generally speaking, right? Us programmers, we start counting from 0. The computer starts counting from 0, so that's a little weird sometimes. But what you get used to it after a while, and so we count from 0, 1, 2, 3, and 4. So that's interesting, right? So there's 5 elements, but we shift everything over to count from 0. 0, 1, 2, 3, 4, 5, those are 5 elements. So something to keep in mind there. And so if you have n elements, if the size is n, you can access subscripts 0 to n minus 1 without ever having any problems. It's always a problem if I look at anything negative or anything that is n or greater, because then you're actually stepping outside of the bounds of the array, and nothing good can ever come from that. Nothing good, I can say. You might not have anything catastrophic, but you won't have anything good that pops out of that. So this is, the same kind of stuff here. I cannot just see out the entire array. I would have to use a loop structure if I wanted to print out every element in this array. Because I can't just say, give me values. This isn't Python. Python would do it. But but we're not Python, so this does not work. Come on, compiler error. What? Oh, yeah. Why? This does it works. What does it print though? It prints a memory address. This is the memory address in RAM where the first byte of values is stored. And so yes, for a brief moment I'm like, why isn't that an error? Yes, but that's because values is technically a pointer, a reference to the first element, and that's what it prints out. But it does not print out what you expect it to print, right? You would have expected it to print at least 99 garbage, 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 but that's not legal. It works, it just doesn't give you anything you expect. Okay, here, so cool with that. And again, this is just meant to kind of refresh your memory. For a lot of these things, this is not meant to go ahead and be a comprehensive guide to all of this stuff. So I could initialize, instead of doing this like this, let me just set up here. I could say, I could put 1, 2, 3, 4, 5 inside of here. You got to make sure you put the right number of elements. You can't put too many. That's an error. And if I put too few, it'll fill the rest with zeros. So I can do something like this. Even though this is 5 elements, I'm filling in the first 4. The last one will be filled in with 0. And I can prove that by putting in a quick and dirty loop. I is 0. I is less than size. Plus I. Print out values sub I on its own line. And so there you see I get 1, 2, 3, 4, 0, because for whatever reason, once you initialize all these, everything else gets set to the default, and in this case, default is 0. And so that is initialization in a nutshell. So a lot of this is just showing you that kind of stuff, but it's filling in respective order as it goes. You don't have to put this like this, because then now this is, instead of making this 5 size, this turns it into a 4 size. But nothing, again, nothing good can happen from this, because, whoops, sorry about that. And then it's because it's a 4-sized array, but I'm telling it to print out 5 elements. So the first 4 are perfectly fine, but when I outstep the bounds of the array, in this case it prints out garbage, it very well could have halted my whole program, because I could have gone and went out of the walled garden there that the array was in and basically struck something in the ground and be like, I'm not supposed to touch that. And the operating system pitches a fit and says, we're done here, and crashes your program. So that's a huge difference there between putting something in those square brackets and not. So that's, just keep that in mind. So again, no bounds checking. We just showed that. You know, like it'll do it. If you tell me get me the 5th element of a 4-element array, it'll do it. But that's definitely not a good thing. Why is that green? I don't know why that. What is that green? Index. Oh, at least gave me a warning about it. Hold on. Yeah, now it went away. I didn't realize that. Yeah. I haven't been using the Visual Studio 2019 for a long time here, and they've got a couple new bells and whistles that I've, to help you along with these kind of errors that did not exist before 2019. So I'm a bigger fan of 2019 than I am of 17. That's for sure here. So again, make sure you never go negative on your index values and never go size and beyond. That's just, and that will cause what we say. And we can always have what was called off by 1 errors. Like I said, we were off by 1 there. So a lot of times it's tricky to know if I've gone, like if I'm supposed to go from 0 to size -1, you have to make sure you do that. You have to make sure you stay in the bounds. And a lot of times there's less thans and less than equal tos. And so sometimes, sometimes we actually have to go everything up to, but not including the last element, not even just the end. And, what am I talking about? I'm just Grandpa Simpson here. But I'm saying there's a lot of times you have to watch out, because you either start and go 1 too few on one end, or you go one too many on the other. So you have to watch out. And this happens to everybody, no matter how experienced we are, especially when we start doing like sorting and all sorts of stuff, when things go crazy with our for loops and stuff like that. And so for something like this, because this is part of the new standard, I can alternately, I believe I can alternately do something like this to print out every element. I can say, oops, I can't say that. I can say for every int I that is a part of values, print, let me just steal this, I don't have to type it all out, print I on its own line. Let's see, will it let me do this? Some of these new features here. Yep, it'll let me do this, and now, like you said before, okay, it'll print 1, 2, 3, 4, 0, and now what's cool about this, a minute ago this didn't work, it didn't work right. If I get rid of size, it'll print correctly. And there's my 1, 2, 3, 4 with nothing else, because this basically is a range-based for loop, and this looks ahead and says if you're familiar with C#, this is, the syntax is different, but essentially I read this as for every integer I in values do. That's kind of how I turn this into English here. And so basically the compiler knows that values has 4 elements. And so this thing goes ahead and basically it's just saying, like we were doing before, for every element in here, go ahead and print out that element. So every time I iterate, this I variable is being replaced by the next element in the array. So it starts with the 1, and then the 2, and then the 3, and then the 4. Each time we come around for the for loop, and this thing automates and knows when it's done after it's iterated through every element in the array, and then we go to do other things. So that's how that works. There's a lot of information about it if it's interesting, but there's other rules, like you should always make this const reference if you can help it. Like this, it speeds things up if I make a const reference, especially for object types and pointers and things like that. So again, just keep that in mind as you go. Now we can just fly through the range-based for loop. And so things like processing the array contents. What if I wanted to go through and basically check to see what is the sum of all the elements? And just like the other loops before, I can say, okay, I can go ahead you can do it both ways here. Let's do it the more complicated way, just to kind of get our bearings here. I can say the sum is 0. For I equals 0, I is less than size, plus I can say sum plus equals values at I. And when I get all said and done, I can say the total is, and then I can print out sum, and I can print out the n-round character. So this will get me the element 0, the element 1, the element 2, the element 3. Let me put the 5 back in here, and then it'll print out 15, because that's the sum of the first 5 integer values. Total is 15, as we're expecting. And so that, again, that handles different elements. And if this is something that you're having trouble with, then make sure, because the first homework is all about arrays and files and a few other things, make sure you get a hold of me through email, and let's talk things through if you're having issues with how you index arrays on both ends, getting and setting the information. That's a big deal here. So a character array is an array like anything else, but it's slightly special in that you don't have to put each individual character separated by commas. You have to do this for integer values and float values and any other thing, but obviously it would make no sense to try to write out your whole name. It would take half a day to write I only have like 13 characters in my name. But still, it would take a long time to every character to be separated, and so I can do this like this. It only works for character arrays. So here's the range-based for loop, as we're saying. This prints out every element, like we were discussing. Here's what I just did, setting up and figuring out. Oh, I could, the total is. Oh yeah, you can start doing that too, and say, okay, that's the total. What about the average? And the average is, and the question is, do I care about losing the precision? And I probably should care about losing the precision, so I should use a double, and I can say double average equals the sum divided by size. And sum is an integer value, size is an integer value. So right now, even though we did all this hard work, and let me change this up just so it's slightly off, so it'll be 3.2. But the average prints out, where's my value there, as 3. Because even though this is a double, oops, let me get rid of this breakpoint. Come on. Let me get rid of that breakpoint here. Let me put a system pause in here. Just so I can't do this. Okay, so even though this is a double, this is an integer, this is an integer, integer division occurs, and then that integer result gets turned into a double. So yeah, so that's weird, right? So I still have to do a static cast over here to turn one of these values into a double so that I can get my 3.2 out of the deal. And so there's my 16 and there's my 3.2. So just keep that in mind as you're working through. So static cast when you need to here. So saying again, they're using doubles, but that's not how you should go about doing things. You should only cast when you have to for the calculations you have to. Because if I used float and the numbers got big enough, then I would actually have some kind of error term. And if I do things this way, I'm not going to have as much of an error term because as I'm calculating everything, the integer value is maintained and stored correctly until the final end. So you can't compound mistakes, especially on the high and low ends of these values. So just keep that in mind. Keep the data types as you need them, in this case as integer values, and only turn them into what you need to at the end of the day. All right, so here is some code that can go through and find me the largest value. As you could imagine, you're basically just starting with the first element and you're going through the rest and just asking the question, hey, are you bigger than whatever I found before? And if the answer is yes, you replace the value, and if the answer is no, you move on to the next until you've exhausted the search, and whatever you have sitting in your little hand there has got to be the largest number. Same with this for just working the other way around to be the smallest number. So object-oriented programming, which is after the first week here in Advanced C++, is a 3-week process, and we use that for the rest of the semester, is a much better way of doing things than the old C way, which would require what we call partially filled arrays. When it comes to filling up data, like how would I go about if I have an unknown amount of data, like an array of objects or an array of integer values? And so we're going to see here the vector is a better way to do this kind of stuff. Like I said, technology has advanced over the years. Thank goodness we don't have to write all the code. We're going to write some code for custom vectors, custom lists, custom sets when it comes to the 3 major data structures, just so you can get a taste for what's going on under the hood. But at the end of the day, once you know what's going on, you will just fall back on the standard template library. So don't worry so much about partially filled arrays. And even using partially filled and parallel arrays and all sorts of crazy stuff. Don't worry so much about this. I don't even teach this in the first course just because when we get to Advanced C++, all it does is teach you bad habits. And if you fall back on parallel arrays and these kind of partially filled arrays, then you're going to have a bad time getting all this to work. Okay, so let's see, parallel arrays. So arrays can get passed as function arguments. They're essentially pointers. And again, we're not going to touch pointers until the next lecture series here, the next video. But basically, you can pass them along. And what's weird is they're passed by pointer, even though you don't see the pointer, you don't see a reference, you see the square brackets. Where's a function like this? Well, come on, give me a function here. Like here, you see square brackets. But that basically tells me it's a pointer. And you can actually replace the square brackets with a pointer, and the code would run exactly the same. Because at the end of the day, that's exactly what's getting passed along, is the memory address to that location in memory. And so what's interesting about that is because I'm passing a memory address, I'm passing a reference, a pointer as a reference, if you want to think of it that way. If I modify the values inside of the function, I'm modifying the real data and not a copy. There's no copies made of arrays when you go from like main into a specific function, or from function A to function B. So you have to watch out. Even though you don't see a little ampersand or a little pointer, you can modify the stuff inside of there. And if you don't want to, this is where it makes sense to put the word const in here, so you don't accidentally change everything and you give it read-only access. I'm allowed to look, like here's a book, you can look in there, but I'll slap your hand away real fast if you try to write in there and change anything. So that's the idea here, you know, const versus non-const and things like that. You can have multi-dimensional arrays, 2-dimensional arrays, 3-dimensional arrays. You just have to understand if you're dealing with row major order or column major order. And we're not going to worry about that in this case. There's 2-dimensional array stuff. Where is, come on, where, keep on going. It's a lot of 2-dimensional array stuff. And then 3 or more dimensions, the computer can do it just fine. Our brain kind of gives up after 3 dimensions because we can think of 1-dimensional arrays as like 1 row or 1 column of an Excel worksheet. I can think of 2 dimensions as an Excel worksheet, and I can think of 3 dimensions as like a cube of information. But then once you're into hypercubes and everything more, it doesn't make any sense anymore when it comes to visually representing the data, but the computer can do it just fine because it's just a bunch of multiplications and additions to figure out what memory address that information is stored in an n-dimensional array. So here is, each dimension gets its own square brackets, 3 dimensions by 4 by, or 3 by 4 by 3 by 4. That's a crazy kind of thing. And so what's interesting here is that for an n-dimensional array, when you're passing that along, you have to supply n-1 pieces of information about the array itself. So that's why for a 1-dimensional array, I didn't have to pass, come back here. I didn't have to pass any extra information of any of the dimensions. Because I'm already passing a pointer and I can figure out all the other memory addresses from that one pointer. But for 2 dimensions or 3 dimensions and so forth, you have to start supplying information about, like for a 2-dimensional array, I have to tell you, or you have to know how many columns are in each row, so it can do the calculations correctly. Or for a 3-dimensional array, I have to know how many rows and how many columns there are, so the math can be done correctly. Otherwise, there's nothing the compiler can do to figure it all out. Okay, so the final step is, usually I laugh about this in class because I'm like, I teach you all this stuff about arrays, and then I kind of tell you to throw it all away, because there's a vector class inside of the standard template library that is a smarter version of this, and there's an array class inside of the standard template library that is a smarter version of that as well. So array is more of a compile time thing. It's a smarter, or like a STD, standard template library array is a smarter array. Vector is smarter than everything combined. And I'm not going to go into too much detail here because we are going to cover this for 2 straight weeks in a couple weeks or a couple class sessions. But just to understand that I can set up a vector, a smart array, and I can use the angle brackets as a templated library, so that I can set up a smart array of any data type I want, just like I can set up an array of ints and floats and so forth and so on. And again, what's cool about this is why I don't teach the partially filled arrays and all that stuff from earlier, is because this thing automatically resizes itself, gets larger and smaller as you add and remove elements from it. So you don't have to worry, like I said, set up 10 spaces, and they go, how many have I used yet? Have I used 3? Have I used all 10? Have I used 0? That's a big problem. And when we go and implement the vector under the hood ourselves, we will maintain that, because someone does have to maintain that, but thank goodness in the standard template library, that's not us. And so for everything else, it's a little more challenging to set everything up for the first time. It's the syntax of initialization using a constructor is different than what you see here for the array. But once you've done that, you can essentially use the vector exactly the same as an array using square bracket notation, and you can dereference you can use the dereference notation and so forth and so on. And so we will go into excruciating detail about all the ways the vectors can be used, and constructors and destructors and functions and pushes and pops and all sorts of things. So I'm just gonna let this, just kind of let this thing slide here. and say, all these functions we will cover, and that covers Chapter 7, and we're ready to move on to the next. Chapter 8 in the book covers searching and sorting of arrays and vectors and collections. We're going to call them collections because you can basically do searching and sorting on any of the data types we're going to use as part of the standard template library. So what are we talking about here? We're talking about there's only 2 ways to search for data. 2.5, I guess. There's linear search, binary search, and yeah, I guess that's pretty much about it. There's a hash you can do later on too. So linear search versus binary search, and the whole question comes down to which one do I use? It all comes down to the only question you ask is the collection, is the array or the vector sorted? And if the answer is no, then I have to search each individual item inside of this thing because there's no way to know one item from the next where the thing is located. It could be in the first element, it could be in the last, it could be somewhere in between, or it could be not in there at all. Or if it's a binary search, if everything is sorted and I'm looking for a value, if I go and I overstep my bounds and I go, oh, my value is too large or my value is too small, then I can basically say, nah, this isn't working for me. And so I can actually break down a problem, just like looking at a dictionary. How many searches does it take you to find a word in the dictionary? It takes 5 or 6 sometimes, right? Because you're trying to find the right page. You open to a random page. Then you go, oh, my word's over on this side because the word I'm looking for is less than the page I'm on. And you work your way down until you find that answer. You don't have to search every word in the dictionary to find the word that you're looking for. So that's the whole idea here. So linear search, again, if you can get away with it, you want to sort your data because linear search, especially on huge data sets, is a huge time sink. And the sorting, as much as that takes time, you're paying for it on the front end versus paying for it on the back end. And when you pay for things on the front end by sorting, you will see that, as we go further into the course, that you pay a price, but you don't pay nearly as much price because you're only doing that upfront one time, and it's a much easier search for every other search later on after you've sorted the data. So pretty simple algorithm. Keep asking, hey, are you the number? Hey, are you the number? You find it, you're done. But if you don't, you could exhaust the search. So it could take, if it's a million element array, it could take 1,000,000 tries to go through and find if it's in there. So here's code, simple code, and that's all there is to it. Easy to understand algorithm, pain in the butt when it comes to the amount of time it takes to find an array or to find an element inside of it. And binary search, again, breaks the problem down into 2 parts. It partitions the search. If it basically starts in the middle of a sorted list, and if it knows it should go to the left or the right, and it goes there, and it cuts the search in half every single time because it's sorted. So if the number's larger than whatever number it found in the middle position, everything to its left goes away because the value is going to be greater. So it breaks its way down. So it only takes, we call log n number of tries, a much smaller number of tries to find out if a value is in the array or not. So basically here, so if I'm looking for the value 17, if I search 11 first, I go, nah, you're not 17, but I can go, I'm basically cutting off the search on this whole half because the number is going to be over here somewhere or not at all. And so rather than search every single value, you're only searching a very small number of them. So it's a little more complicated when it comes to the algorithm, and we're going to actually do a recursive version of this later in the term. Not that we have to by any means, but you'll see that we can use binary search. Here's some code for it. I do it a little, everybody seems to do it a little differently, but there's the code that makes it work. And again, you have to make sure it's sorted. Nobody's going to check for you to see if it's sorted, but if it's not, you're not going to get the results that you're expecting. It'll be a runtime error. There will be no compiler error or anything, or a warning to tell you, because there's no way to know that thing is sorted or not. Trade-off, you have to sort, but it's always going to be better. So for like a 1,000,000 sized array, a linear search, as we discussed, could be 1,000,000 searches. And let me see, 10, 10, it could be 20 searches, I believe, for a million sized array, log n, 2 to the n power. I think 2 to the 20th power is about a million, because 2 to the 10th is about 1,000, 1,000 times 1,000. So instead of testing a million, you would test 20 values, and if you can't find it in those 20, it doesn't exist because of the way the algorithm works. Okay, sorting. There are many different ways. There's only 2 ways to search, but there are many, many ways to sort. And so we generally teach in the first course the simplest ways, which make sense, make the most sense logically and are the easiest to put into code, but they're the worst algorithms because of their complexities. So like bubble sort and selection sort and insertion sort, they are usually what we call n-squared algorithms, and the ones we can use with recursiveness, like merge sort and heap sort and quick sort, those kind of methods use a much more smart way of doing things and break down to n log n comparisons and swaps and all sorts of stuff to get the job done. So sorting, you all know how it works, and I remember sorting all sorts of stuff over the years, DVD collections or CD collections, all back when these things existed, and so forth and so on. So bubble sort is about the worst that you could get. There's a newer version of it that's better than the way I was taught when I was a kid, but essentially you're just kind of going through elements and just checking to see if they exist, and if we need to swap elements. And essentially we go through all the elements, we make a pass through, and if we never swap anything, then we know the thing is sorted. If you're going through 1 is less than 2, 2 is less than 3, 3 is less than 5, but 5 is greater than 4, I have to make a swap. And so I keep going through pass by pass, adjacent element by adjacent element until I make a full pass with no swaps. And then I know that I've sorted everything out. It's the easiest, it's one of the easiest conceptually, but it's one of the slowest because it just does so many swaps and so many comparisons compared to smarter methodologies. And so they call it bubble sort because the values take time, especially from the bottom up. They can only move up, they can only bubble up one time per pass. And generally speaking, the larger numbers fall to the bottom. So in one pass, the largest numbers jam to the bottom. And then the next pass, the second largest numbers jam to the second spot, and so forth and so on. So you can improve efficiency a little bit on the algorithm, but it's still not very good. Okay, so selection sort, basically it's better than bubble sort, but it's still not great because selection sort goes ahead and makes a pass through and only makes one swap per pass, because it goes, okay, I'm trying to find the smallest element, and whatever it finds, it's going to find that location and it's going to swap the value with the first element. And so in this case, we know when we go through everything, we only instead of making swaps all the time, we make one swap to get the smallest value to the first element, and then we know that is sorted and we can move on and we can make the problem a little smaller, and now we can find the smallest of everything that's left, and so forth and so on. And so it's basically bubble sort without all the swaps. It's still doing a ton of comparisons, but instead of doing a whole ton of swaps, it's only doing basically n swaps, one per pass as it goes through the list. And so that is selection sort. And then there's insertion sort, and there's other kind of sorts. There's 20 or 30 or 40 of them, and maybe all of them have yet to be completed. Some of them are weird ones, are just conceptual and just theoretic, and they would never be used for any real purposes. So sorting and searching of vectors. Again, the standard template library has algorithms and collections. All of this at the end of the day can be done for us. But we have to understand, of course, that especially when it comes to sorting, that there's generally general use algorithms used for this. We don't really 100% know which sorting algorithm is used under the hood to get the job done. Generally speaking, it's a hybrid, but it uses certain algorithms for the first step, and then when it gets to smaller problems, it uses a different algorithm. but you have to do research into it. So if it's one of those things where, certain data sets work well with certain sorts, you would have to go ahead and find those library functions to plug them in, because then maybe your collections will sort faster because you know more about the data than the general use functionality does. But again, std : sort does all the hard work. There's linear search and binary search already in the standard template library. We do not have to implement any of this code to do that kind of stuff. So that covers this chapter. We have one more chapter to go. I know I'm bald, but that's just my green screen going through my hair anyway. So one more chapter to go and we are done with our review. All right, last chapter here, chapter 10, a quick discussion about string classes and characters and the functions that apply to all of them. And again, strings are just modern day fancy character arrays sitting under the hood. Oops, don't mind that. It's a completely different class. So here, character testing, there's a bunch of functionality that can tell you if it's an alphanumeric, if it's a digit, if it's lowercase, if it's uppercase, if it's a punctuation character, and so forth and so on. How often do you use these things? Not too often, but they exist, and they're part of the C language. They've stuck around since C. I don't think they've been updated since then, so you have to watch out. They're a little different than what you might expect. But you can write code to handle this. Is it an alpha? Is it a digit? So forth and so on. Conversion of cases. What's weird about this one, there's no function to handle an entire string. You would have to write the functionality yourself to take a string and convert every single character. And if that's changed, please let me know. I would love to use that. I just haven't seen it yet in the standard template library. So to upper would change a lowercase h into an uppercase h. It would leave an uppercase h alone, and it would leave the exclamation point alone as well, because could you imagine there's no such thing? What's a capital exclamation point? There is no such thing. At least there isn't yet in 2020 as we're doing this kind of stuff. So just keep that stuff in mind. To upper, to lower. And generally speaking, when we take a string and we want to do string comparisons, we basically take both strings and apply the same functionality to it, so that if a user typed in a capital letter or something when they weren't supposed to, or so forth and so on, we can reduce or turn everything to uppercase so the comparisons actually work out. Because a capital A and a lowercase a are not the same ASCII value. They will not compare correctly, even though in a lot of cases they should supply to they should become the same letter, so the comparison should be equal. C strings. So again, this is the old C style string, which is a character pointer, constant character pointer, or character array. And so there is functionality sitting under the hood that requires old C strings. So the string class can supply that to you. And so the string class, there's no guarantee there's going to be a null terminating character under the hood, but for a C style string, I need that. So among other things, you need to have these kind of conversions in some places. I know I had to use this back 10 years ago when I was working in code. So just keep that in mind again when you're dealing with that. When things go wrong, it's .c_str. I wonder if they're going to show it here. In the string, no, I guess not. And there's no reason to really worry these days about the C style strings. You'd be taking a C class and then a C++ class if that were the case. So other than just understanding and knowing that there's there's an adapter that can get me from C++ to C and from C to C++, I guess that's all you really need to worry about. This is probably going to be a very quick lecture. I'm probably already more than halfway done with the talk here. And so where is it? And so I can convert this. This isn't so, we don't need this so much anymore. I guess we do, yeah, I guess, because there are new toString functions. We can take an int and convert it to a string. We can take a float and convert it to a string. But we also need functionality that can take a string and convert it into those, back into those other data types. And so one thing you have to watch out for, some of these are portable, meaning if I make this code available for different compilers on different architectures in different implementations of a compiler, some of these functions won't work properly, or some of these functions aren't even guaranteed to exist. So, and I don't know them offhand because we don't use them very often. And when I do, I look them up to make sure I'm using portable code. Because especially out in the world, you never know if you're going to be porting your code to run on a different system one day. You don't want to have to come back, spend that 1 minute of research now so you're not, having a bug or something or a compiler error months or years down the road that you or hopefully someone else has to fix for you. So these functions, A to I, like ASCII to integer and so forth and so on, those kind of functions. So lots of different functions to do all the work. And they all make sense, string to integer, string to long, and they all make sense. They all sound funny, right? Stool. Give me a stool. Give me that, whatever. But you get the point here. And here are all the toString functions that can get me back to string from those data types. And so my own C string handling functions, again, this very rarely happens. And when it does, that's what Stack Overflow is for. Just find a quick and dirty solution to some of these things of how I can take character strings and copy them and so forth and so on. And there, like even for this, there is a fast and really quick and dirty way. You can do it in like one-liner. While, blah, 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 increment, yeah, whatever, who cares, right? So just understand that you can, if you're running old C code, you're going to worry. But as we get further and further into the future, we don't care. More about the string class. We'll talk about this as we go because string is part of the standard template library. String is just a fancy character array or a character vector, if you want to think of it that way. So once we get introduced to the syntax and the API of some of these collections, basically string will just pop into your head for free because almost all of the functionality found in those classes work for string as well. So we can just kind of fly through that understanding. I don't know, is Wheels of Fury a good movie? One day I will try to find it, I guess, but not today. And so you can input, nowadays you can input into a string using, you couldn't do this a long time ago when I was a wee lad, but now C++ has, advanced to the point where I can actually input a string using the cin operator. Cool stuff. And I can use getLine to make it work as well. String comparisons are simple for standard template library strings. The old days, they were a big pain in the butt. You had to use all these special functions, which I probably slid right by, and I don't necessarily care about. And so, but you can test for all the relational operators for string, just like you could for anything else. No need to worry about constructors for strings just yet, but you can make it work. Here's all the relational operators. Here's some more stuff. Here's a hot dog on a bun. And I think that's about it. And all these member functions we will discuss in the vector class and so forth and so on. And we will get used to this. And again, comes for free. All good. Part 3 is done. The entire 3-part series is done. It only took a couple hours to go through the introduction, but a couple hours versus the 40-something hours of study you've done in that course, it's a good review. So, parts of it are good, right? So parts of it aren't going to be great as I'm flying through things. So as always, if something isn't clear to you or you need a better explanation, just send me an email, send me a comment here, of course, on YouTube, and I'll get back to you as soon as I can. This is a first video in the series, so I'm excited to move on here. The next video will begin covering object-oriented programming. And before we do that, we will cover pointers because we need pointers for more advanced functionality in C++. And then we also need to understand structures because structures are essentially like the baby version of classes. So if we take these couple steps early, as we move further and further into object-oriented programming, everything will just kind of fall into place and work out for us. So I'm looking forward to these videos, looking forward to hearing your questions and working with you guys. So we'll see you next time. Thanks. Have a good night.